Welcome, students. This lecture, we're going to be talking about the history of the environmental movement. Environmental studies and environmentalism has roots that go back, hundreds of years. Officially, probably the main players that we can learn from that shaped our thinking about environmentalism probably came about in the 1800s. We started keeping track. So I want to go back and look at the first main players that gave us the shaping of how we think about environmental studies and how we think about preservation and conservation, two kind of different things in the environmental philosophy. So we're going to go back. Remember last lecture we talked about stages of environmentalism. Stage one was that pragmatic utilitarian conservation. Okay, that meant using resources for people's good, maybe conserving the earth and the resources, but for the greater good. Stage two was that preservation, aesthetic preservation concept, and that is valuing environmental resources for their inherent good, preserving and not using. This is more like the nature philosophy of keeping things intact. So we're going to look at the different viewpoints in that matter and then move on and talk a little bit about the ethics behind different thinking. Alrighty, so here let's look at these dapper fellows on our first slide. We saw these guys before. We're looking at Teddy Roosevelt, one of the earlier US presidents, named the teddy bear after him. Good story for another time. And his buddy Gifford Pinchot there on the top. These gentlemen were of the conservation philosophy. Let's use it and conserve it so we can use more of it for the greater good. And on the bottom two spaces here, we see John Muir. This is the founder of the Sierra Club in the 1800s, maybe the original granola, as I mentioned before. And this gentleman on the bottom right, Aldo Leopold, another preservationist thinker, not talking about using and saving resources for our benefit as people, but preserving the Earth's resources for their own inherent good. They deserve and have value to be kept intact. Early progressive thinkers. All right, moving on here. So let's talk about Gifford Pinchot, Teddy Roosevelt, and the government, the US Forest Service. Let's conserve for use. Starting with Teddy Roosevelt, a lot of people consider him an environmental president. Well, he did do a lot of early conservation for the country. He was very good buddies with Gifford Pinchot, whom he actually made the head of a governmental agency, the US Forest Service, when it was brand new. So Teddy Roosevelt was a hunter and a sportsman, and he did love the environment because he wanted to go out into it and hunt, get the big game of North America. Roosevelt did establish 150 national forests, many bird reserves, national game preserves, and 5 of the earliest national parks, and I've got them listed here on the slide for you trivia buffs, okay? 18 national monuments, and also just many million acres of public land. And I include a little note in here. The Obama administration actually doubled that amount of land with over 550 million acres put in preservation status, okay, not to be used. So talking about environmental presidents, Obama gets the gold star for that one. So Teddy Roosevelt did a lot for the early environmental policy of our country because he wanted to use the resources. He wanted them to be saved so people could enjoy them. Gifford Pinchot had that similar thinking. He was, and I want students to remember this, a conservationist, okay? He was also a professionally trained forester, learning and teaching the management of timber, of forest land, to use it for wood and all types of resources, cut it down, and then learn how to regrow the groves of trees so they can be used again, managing the forest, okay? First chief forester of this new Forest Service in the country. The guiding principle that forests could produce timber and be maintained for the enjoyment and use of future populations. Okay, this is the conservationist philosophy. All right, and by the way, Pinchot became the governor of Pennsylvania later on in his career. I think it does not hurt to know and be friends with a good president during your tenure. Talking about the great case study of conservation versus preservation is the battle for Hetch Hetchy Valley in Yosemite National Park. John Muir, the original preservationist leader of the Sierra Club, versus Gifford Pinchot, the conservationist, the user of resources, and let's conserve them for future use. So we have the first epic environmental controversy in the United States, pitting John Muir of the 1800s, the original environmentalist, against Gifford Pinchot and the city of San Francisco. Going back, John Muir, actually, you can thank this gentleman for Yosemite National Park being what it is today. He lobbied with the early Sierra Club, which he created, for Yosemite to become a national park, and it finally was. He had a little bit of power back then for an environmentalist. He also advocated for Hetch Hetchy Valley, beautiful valley within Yosemite Park, to remain preserved. Okay, that was his main legacy. Unfortunately, it did not go so well for him and Hetch Hetchy Valley in the end. Now, in 1901 to 13, he led Sierra Club in a huge campaign to protect Hetch Hetchy Valley from being filled by a huge reservoir and a dam. He did not want the valley to become dammed and all of the water backed up into the valley and filled like a giant pool, a giant lake, for use of future people of the city of San Francisco. Now, how did all of this battle occur? Well, in 1906, San Francisco had the enormous earthquake and fires that it's known for now. After that, there was a huge push for more water supply. Tuolumne River and Hetch Hetchy Valley was the #1 place San Francisco looked to. Gifford Pinchot, then the first head of the Forest Service, campaigned for the city. He went around and agreed that there would be great benefits to damming and flooding the valley and taking away those natural ecosystems, filling them up with water, because it would provide the greatest good for the greatest number of people. That would bring a huge water resource into San Francisco by pipes so they could use it in the future in needs, when there was need for water, for fire problems, for earthquake, for shortages. So the debate continued for years, and the whole country read through the newspapers what was going on with the great debate with Hetch Hetchy Valley. Let me get this in the frame. So these fellows here don't look that dissimilar. Up here you see John Muir in Yosemite, looking very introspective and probably thinking about his campaign. And also over here on the left, we have Gifford Pinchot. And these gentlemen did know each other and they were civil with each other, but they had opposing viewpoints about conservation, preservation, and ultimately how Hetch Hetchy Valley would be used. Now, after many years of lobbying with the Sierra Club against the filling up of this beautiful Yosemite Valley, John Muir and the Sierra Club failed. Hetch Hetchy Valley was flooded and a reservoir created and the water piped into San Francisco. President Woodrow Wilson signed the Raker Act in 1913, permitting the flooding of Hetch Hetchy Valley for, quote, the public interest. Now, this shows that Gifford Pinchot's philosophy of conservation, of, yeah, we can protect the environment, but it's only going to go so far. We need to be able to use it for public good. So all of those thousands, hundred thousands, millions of organisms and ecosystems that occupy the Hetch Hetchy Valley, thousands of acres, were flooded out and moved, either relocated or killed, and removed from the situation by the reservoir and the water filling up. And that dam is still there, and the valley is still flooded, and that water is still today used for San Francisco. The O'Shaughnessy Dam was completed in 1923. It took a long time for this project to be completed. And alas, John Muir died 4 years before construction of the dam even began, although he did know that his cause had been defeated. Okay, but the legacy of John Muir and the preservationist movement continued on. We still study his philosophies today. The preservationist philosophy that nature should be kept and preserved untouched for its own good, not just for our public use. Maybe for our public enjoyment, as in don't touch, just enjoy. Go through a hike and enjoy the water. Hetch Hetchy Valley, up here we have early 1900s. This is before it was flooded. We see the valley nice and low, and you can kind of find markers and points to compare this photo to the photo of a current Hetch Hetchy Valley with the reservoir higher. Okay, the valley was flooded, the water level rose up, and you can see, looking at different markers of height, that the water is definitely higher and flooded out. Many ecosystems lost when you are flooding valleys and areas with dams and keeping that water for reservoir. And we'll talk about dams and their consequences later on in the semester. Now, back to the different philosophies of environmentalism. Aldo Leopold is in the same camp as John Muir. This gentleman was also from the 1800s, and he helped create the philosophy we know as the land ethic. He was an author, an ecologist, a preservationist, many things. And he wrote that land is a community. It's the basic concept of ecology, but that land is to be loved and respected is an extension of ethics. So Aldo Leopold learned to bring together ethics and philosophy into science and ecology. Okay, so in 1935, he and his family actually took on a huge experiment. They went out and used a nice area of dilapidated farmland as a summer vacation spot for themselves and decided to restore it, and planted thousands of trees over many years, and actually wrote about the experiences of that ecology and that process in a book. He authored one of the most famous environmental books to date, known as the Sand County Almanac, to document what he experienced during those years. He experienced a lot of ecosystem interaction, a lot of organisms, a lot of restoration after planting many, many trees on an area that had previously been ransacked for agriculture by the Wisconsin University. So Aldo Leopold founded the land ethic, a term I want my students to know for all quizzes. The land ethic said that a human community should be enlarged to include non-human elements like the soil, the water, the plants, and the animals. Let's include the land in our society. Here's the key. People must view land as a community, not a commodity. So as in opposition to Gifford Pinchot that saw the U.S. forest as commodity, using that timber and those resources for greater good, for economy, and conserving so we could use it again and again. Folks like Aldo Leopold and John Muir said, no, we must preserve this not as a commodity, but something that has inherent ethical value, worth on its own. He also said, well, economic well-being can't be separated from the well-being of our environment. We need our environment to be intact for our economy to be intact. So Aldo Leopold did open up the question of ethics when it comes to the environment. And I want my students to understand what exactly it is, this term ethics. Well, it's a branch of philosophy concerned with what actions are right and wrong. We're talking about environmental ethics. That deals with our moral obligations to the environment around us. Do we have any obligation to keep our environment in good condition? Or do we just use it and make sure it can stay just intact enough for people's use in the future? Worldviews are a set of basic beliefs and understandings that shape how we see the world around us. So we could say that, a Trump administration in the United States has a certain set of worldviews that includes his environmental thinking, their environmental thinking, and the way they see ethics. And then the progressives or the Democratic Party might have a different set of worldviews, a higher set of environmental ethics that maybe view things like climate change differently and would lead to a different environmental policy. So talking about environmental ethics, we need to ask the question, who or what has moral value? What has value? Well, value is a measure of the worth of something. We can have, as the preservationists liked to think, inherent value in ecology and the environment. That's the intrinsic right to exist, its innate worth. Or we could take the camp of Gifford Pinchot and Teddy Roosevelt and conservationists. We could say, well, the environment has instrumental value. The items have worth only because they are of use to a person or a community. Now, there are different levels of moral consideration and value, and it's good to understand the context of that in environmental science. So at the top here, we have how highly do we value things in our realm? Well, at the very top, you might say the highest scope of moral consideration is me. I hope that I value myself pretty highly, maybe even higher than anything else in my life. Moving down, you might find immediate family members, morally considering your family, maybe after that all of humanity. Maybe a little less would a person value animals and organisms. Certainly you would assign higher moral value to your family than you would a fox that you see in a jungle or forest, okay? Even after that, maybe all life on the planet, a little more obscure, not quite the value. And then even less moral consideration would be the entire planet. It's hard to care about something like, well, the planet, as much as you care about your parents or yourself. Many of us can agree on that. Well, switching gears away from our environmental thinking and how it grew to be in the different stages, I want to start moving forward and thinking a little bit about the other end of environmental science, not just the philosophy, but actually the science part of it, and give you guys a little foundation of what we're going to be doing throughout the semester. So we just gave you some outline of our philosophical thinking within environmental science, and now we're going to give you a little bit more of the systems and modeling thinking of environmental science. We're going to be tackling both during this semester. I like to show my students this picture. Looks like a gentleman on the beach. I used to think he was setting out sample containers to do some scientific sampling, and I like this slide. But looking closely, what do you see? It looks like maybe he's setting up an art installation of some sort on the beach, possibly with ocean garbage. So it's kind of bringing together the world of science and the world of environmental thinking and cleanup there. Maybe he collected all that garbage, that pollution, and is making a statement with an artistic installation on the beach. All right, science is not boring, everybody. But what is science? How are we going to be looking at science in the context of environmental studies? Well, a process for producing knowledge is science. But we have to do this methodically and logically, not philosophically, okay? Real true science depends on making observations. You have to see this of natural phenomena, okay? Working about paranormal psychology and things of this sort aren't technically science because I cannot observe it with my own two eyes. Science is a cumulative body of knowledge, something that we build upon and upon over many years by many different scientists. And science is a way to explain to others how the natural world works and meets our needs. So just really briefly, let's think about science and hypotheses, theories, and law. I want students to understand that the way we create scientific theory and law is by first testing our observations. Okay, if we see that the world is becoming hotter over many years, we need to start doing tests and experiments to find out if climate change is indeed something we need to be watching out for. And that might lead to a scientific theory, an explanation supported by a large number of tests. Yes, the world has increased in temperature over the past 500 years. Yes, the carbon dioxide level in the atmosphere has increased by a proportional amount in so many years the same. Yes, it appears that those two things are connected. Okay, that's a scientific theory, considered by experts to be reliable. Okay, now a scientific theory can be pretty heavy duty, like the theory of relativity, the Big Bang theory, or even the theory of evolution. Okay, these are all theories that will probably always remain theories. They don't necessarily include a mathematical equation, but they've been tested many times and agreed upon by scientists. Then we have the camp of scientific law, and it is good to understand that this is a little bit different than a scientific theory. Theories will never become laws. They will always remain theories. Okay, but a scientific law usually will contain some sort of mathematical statement. We're talking about hardcore science that can be proved. Example, E equals mc squared. Laws are the rules and evidence that we actually use to form the theories often, okay? And laws can also assist with the development of these theories. How's that? Thinking about the law of gravity, the law of thermodynamics, of inertia and motion, we're using mathematical equations to help us through. So we have our climate change theory that's been tested many, many, many times, but it's a little bit different than a scientific law. We don't have a law of climate change, right? So there's a little bit of a difference in science. Now we're going to be looking throughout this semester at different environmental systems. These are actually networks of different components and processes that work together. Okay? Things like materials and energy flow through one part of a system to another. And I'll show you an example in a moment. This is a huge concept within environmental science. Systems, ecosystems, climate systems, geologic systems, economic systems, okay? Hey, even political systems. But we're talking about things and components that work together to make something happen. Components of a system. In the context of environmental science, we'll be looking at things like variables. Now, I'm not going to ask you to remember this for a quiz, but I want you to have an idea that state variables store resources like matter or energy. All the different players could be called variables, okay? Well, what happens in this system here that we're looking at? Well, let's take a look. We have the sunshine giving us energy for the plant to conduct photosynthesis. From there, the plant is eaten by the animal, an herbivory. That energy is given to the animal, which in turn gives that energy to a predator animal, which in turn dies and gives their energy to decomposition, bacteria and fungi. That energy in turn goes up as gases after they decompose and after they're creating gases, back to the atmosphere to be used in photosynthesis by the plant again, which is using carbon dioxide. A fantastic system, an open system using components from the outside world. Here's another version of a similar system here, an energy system, a fish tank. We've got sun's energy, light energy coming in. We've got a fish here using food, using oxygen. We've got nutrients and carbon dioxide leaving, and we've got those very things being consumed by plants, which are in turn producing oxygen, which is in turn being eaten along with the plants by the fish. Pretty good little cycle there. Pretty good system. I'm not going to ask you to remember this for a quiz either, but again, this is fundamental stuff to remember for environmental science. A system can be closed or open. Most systems are open. They exchange matter and energy with their surroundings back and forth. Very few systems are closed, totally self-contained, no matter or energy moving back and forth. This might be, if you want to take a micro example, like a thermos. Okay, it's not letting any heat out, it's not letting any cold in. It is shut and closed. Maybe in a scientific experiment like an ecosphere that keeps all of the outside system elements out so it can just contain its own experiment with no input. Definition here, I hope it's not too obscure, throughput, it will be good for you all to know as students. That's the energy and matter that flows into, through, and out of a system. Okay, so you've got sun's energy in, you've got carbon dioxide and all of these different elements coming in, and you've got things coming out at the same time, and that's in a loop. Let's talk a little bit about positive feedback loops and negative feedback loops in science. Please note this for your notes in future quizzes. This is one of the very important concepts in environmental science, and actually it does pertain to climate change pretty often. Positive feedback loop is something that's actually a self-perpetuating process, something that feeds off of itself and becomes more and more, okay? It's an increase in variables that leads to a further increase. An example of a positive feedback loop, well, let's say you have a hot world due to climate change. A hot world is causing glaciers and the ice to melt. Well, that makes the planet hotter when all those glaciers melt. How? Well, there's less beautiful white ice to reflect that heat back to the environment, up to the atmosphere. So that melt actually increases the heat, less reflection, which actually increases climate change, making things hotter, making more ice melt. A positive feedback loop is a perpetuating loop. So your memory aid for this term is positive perpetual. It perpetuates, okay? Another positive feedback loop example, climate change causes drought. That kills plants, and that makes climate change worse because the plants aren't able to absorb the carbon dioxide if they're dead. Okay, plants are a way to keep carbon dioxide out of the atmosphere. But if climate change is killing them, they can't help decrease climate change. It becomes worse and worse in a positive feedback loop. Now, on the opposite end, we have a negative feedback loop. This is when events in science are counteracted and actually backed up and made less. This actually can help maintain stability in systems, and this does happen very often in biology and science. Examples? Well, we have some predators. We have some foxes that eat rabbits. Those predators eating the prey actually reduce the prey numbers. They reduce the number of rabbits. And those in turn keep the predator numbers in check. The less rabbits there are, the less predators there are. So you can see that that kind of creates a balance. When your predators are eating the prey's gone, you can't get too many predators, and you won't get too many prey either. That's a negative feedback loop. Okay. Now, of course, along with all this wonderful valid system science, there will be in our lifetimes much invalid science. And it's good to know when we see or hear science that is not real. Kind of like you might see something fake news and you want to be able to pinpoint, hey, wait a minute, there's something fishy about that. So invalid science are scientific claims based on experiments that can't be reproduced. That means, sure, I could say that I got an outcome from this one experiment, but could I do the experiment again and again and reproduce that outcome? If I can't, it's not valid science. Or science could be contradicted by later experiments that can be reproduced in a different way. Yes, we have a little bit of a crisis in science right now. We're having trouble picking out the real from the not real. And many scientists, they refer to this as a replicability crisis. That means many experiments and research papers don't stand up to further studies, or even the same study when it's reproduced, when it's tried again. There's an increasing concern about the results that can't be reproduced. Can it really be science if I can't get the same result you do when trying to claim something from a test. Now, does this mean that the results aren't valid? Well, that might be a case-to-case basis. Example, studies of the toxic effects of a pesticide on plankton in the ocean. Okay, well, if I can't replicate how much it takes of the pesticide to kill the shrimp over and over again, well, does this mean it's not occurring or it's not real science? Maybe not, but it means that we need to find a way to replicate that data so we can make a real scientific claim. Now, what is the cause for this crisis in replication? Well, many think it's our new technology age. Temptation to produce new science, headlines, results, a publication bias. Journals are prone to publish big results rather than results that say, well, we couldn't really find that this plankton was killed by this pesticide when we reproduced. So instead, they just won't try to replicate the experiment. They'll go to print the first time they do a test and make claims. There are just too many sources to satisfy with new data, so many studies are coming out without taking the time to make sure the data is valid. Now, on the opposite end, many scientists believe that this is not a real crisis because many things in science can't easily be reproduced. So this is an ongoing debate in science and environmental science. But let's take a minute to take a look and try to see different ways you can ask the question, is this data real? If I'm reading a newspaper, is this scientific claim real? You might want to ask yourself the questions in this table. This is actually a table from your textbook, the 13th edition. You have the 14th edition. Questions for baloney detection. 7 questions to ask. Number 1, how reliable are the sources of this claim? Is there reason to believe that they might have an agenda to pursue? Maybe not being totally objective. Number 2, could this data be false if maybe the claims haven't been verified by other sources? Who is there to back up your claims? What data are presented in support of your claim? Number 3, what position does the majority of the scientific thinkers hold? Okay, if there's only one scientist that's making a claim on this environmental science, well, you've got to think, well, why don't the rest of the scientists agree? Number 4, how does this claim fit with what we know about the world? Is this a reasonable assertion, or does it contradict other scientific theories? Many times theories need to work in concert with each other to be legitimate. How else do you detect baloney in scientific data? Well, number 5, are the arguments balanced and logical? Have proponents of the position considered other points of view? It does help to offer different viewpoints when putting ahead of yours. Number 6, what do you know about the sources of the money for a particular experiment or scientific position? Who is the financier behind the study? And number 7, something else to ask yourself if you're looking for baloney in science. Where was the evidence for other theories published? Has it undergone impartial peer review? In other words, has somebody else in the community looked at this and judged it? Or is it only in one publication or so? Okay, so actually, this table is going to come in handy as you all get ready for your environmental portfolio project in a few weeks, where you're going to start judging articles for their legitimacy and looking at different viewpoints of environmental issues. So for now, that concludes our lecture 2. We will see you back for the next lecture. Have a great day, students. Email me with any questions.